All right, so we are on system memory and CPU. You know what we're gonna do? What do we always do? Every time we come in here, what do I do? I draw.
Indeed.
Because I'm hoping that if I draw this, when we do the project, and we're gonna do my project.
You draw to show what the lessons are about.
That's right. So what's right here? How many times have I done this?
About 1,000,000 times.
Okay. What's over here?
Round.
Oh, have mercy. Right? RAM, chip, RAM, processor, that's what we got. Storage.
Yeah.
Right here. Let's call it storage. That's storage. All right, now with storage, you need to be, the technology inside the drive can be magnetic
Or solid state.
Q. Solid state. I just SSD. How about that?
What's under SSD?
Solid state drive.
What is that?
I mean,
What is SSD?
Solid state drive.
Solid state drive.
We're on top.
Huh?
This we're on top.
Magnetic.
Magnetic.
Go and look at your notes. Magnetic. Everybody look at your notes now. Did you write this stuff down? You know? You just hear, right?
Huh?
Y'all know. Y'all don't remember me. Remember me. So there's an interface. There's an interface. This is the technology inside the drive. Technology inside. Technology. If I open up the drive, it's either going to be magnetic, solid state, or hybrid. I'll be honest with you right now. Your drives right now, as of 2025, there's no hybrid. Yeah, they're mostly SSDs, but you know, in the cloud, they still use magnetic drives because what happens is, let's take an example, AWS. When you store information up in the cloud, I'm talking about your business. I ain't talking about this play stuff y'all do, right? You get free storage from Google. You ain't paying nothing. That's play. But I'm talking about if I'm a legitimate company, I'm a legitimate organization, I'm the Department of Defense, and I'm paying for cloud service. Now I need to archive. If I need to archive tons of data that Musk co-worker, Big Balls, stole all your social security information and put it in the cloud. I have to store that and archive it. Archive means back up, store it for a long time. I'm probably going to use magnetic drives. Magnetic drives, not solid state. You tell me. You tell me. That's a good question. Why is that? Why would I use solid state versus magnetic? What did we say about solid state? We know it's fast. It's lickety split fast. What's the weakness? Okay. This is 11:22, so I'm gonna give you a break. If you were networking, then I'd be on you. Because that means you need to start doing research. Just don't take what I say, you gotta do research. What happens, the difference between these two technologies is you keep writing to a solid state drive. You keep writing to a solid state. A solid state drive is just some chips. There are chips on this thing. And if you keep writing information to that drive, you're gonna kill it. It's gonna die fast. Eventually it's gonna die. So if you have a program that's constantly writing data to the drive, and if it's a solid state drive, you're gonna start having holes on your drive. When I say holes, you won't be able to write anything to it anymore. It's just the way the technology is. It's gotten much better than it did like 10 years ago, 7 years ago. It was awful. It's like, why are my drives failing? Because it's solid state. The technology is awful. Whereas magnetic is different. Magnetic has been around since the 1900s when they used to have, you know, I guess y'all don't know. Back in the day, we had like a recorder. We used to record stuff on a, I don't know what you call the thing, mic. What is it called, a dang thing? It's so old. In the old days, you used to have vinyl. a vinyl
Record player?
Yeah, record player, thank you. And you put information on it, you put a song on that, it just lasts forever. Well, not that, but it lasts like, I got some old stuff at my mom's house for the OJs and Kool in the Gang. It's still playing. How long ago was that? Don't answer that. The point is, magnetic technology lasts a long time, whereas solid state doesn't. So now you see the difference between the two? So, if you're archiving, here it comes, if you're archiving data, I'm the Department of Defense, and I need to archive some data about the people I killed in Vietnam a long time ago. Archive it. Which one will I use? Magnetic or solid state? Okay, now we cooking. All right, now we can continue, right? Okay, so our interfaces, we know the technology, but the interfaces is how I get the data on and off the storage. We got PATA, P-A-T-A, that's a ribbon cable, right? Remember that? Ribbon cable? Yes. And the other one's called SCSI, S-C-S-C-S-I, SCSI. That's a ribbon cable on steroids. It had a whole lot of little connectors on it. Put the storage onto it, right? Then the other one is SATA, S-A-T-A, SATA. And that's not a ribbon, that's like a little thin cable. Right? And then the one that my man talked about is called NVMe, or another name for that is M.2. M.2. Okay, so that's storage. Two things about storage. One is the technology inside the drive, and then the interface. How do you get that information on and off the drive when you connect it to the motherboard? In other words, what's the cable look like? Cable, 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 no cable.
Whoa.
Cable, 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 no cable. This is no cable because you take the storage, it's flat, real thin, you put it on the motherboard, you screw it on, daddy. Yes, sir.
What's the word underneath? S-A-T-A? The
S-A-T-A.
Yeah, the N word underneath.
N-V-M-E. N-V-M-E.
NVMe. What's that stand for?
I don't know. Look at your notes. Okay. Look at your notes. I'm too old. I can't remember this stuff. I'm not trying to be snarky. I just can't remember, man. I'll be honest with you. NVMe. Blue.
Non-volatile memory express.
Non-volatile memory, blah, blah, blah.
Express.
Express?
Yes, sir.
Let's see. Storage. 839. NVMe. I gave you all this, didn't I? Yeah. Let's see. Yeah. Non-volatile memory express. NVMe. Right?
Yes, sir.
And it looks like, there it is right here. It looks like this. There it is. That's a hard drive right there.
Yep.
There it is. There's no cable. Did you see a cable?
No, sir.
No cable. It's gonna be fast. Why is it gonna be fast, Mr. Darrell? Because you're plugging the sucker into the motherboard. There's no cable. Where's the ribbon cable?
There's no.
You see the ribbon cable? Do you see the SCSI ribbon cable? Do you see a SATA cable? What do you see?
Nope.
A connector. You connect this hard drive. This is a hard drive. It's solid state. This is solid state. Is this magnetic? Let's see. Is this magnetic?
No.
Do you see anything circle around? Do you see magnetic anywhere on this?
No.
Solid state. So that tells you something about NVMe. NVMe says, hey, the interface, this is the interface. This is the NVMe interface right here. No cable. So the technology inside the drive has to be solid state. Come on, y'all. This is not rocket science.
No, it's not.
Okay, let's do this. All right. Now, are we finished? Did we finish? We just yapping. Let's see. Storage. I don't know what this is. We did storage. We did processor. We did RAM. Let's see what else did we do? We gotta add some more crap, right?
Mm-hmm.
Okay, stand by, so we can hurry up and get this stuff out of the way and leave. It's a short day today. How many labs we got? Who doing the lab? Man, you just can't just keep going, man. You gotta get somebody else. I love you though. You should do my networking class. You'll stop doing that. But I love you. Okay. Processor, RAM, storage. You know we got a whole bunch of other stuff on this motherboard, man. Come on. Let's see. We got these little PCI thingies, right? They come in different sizes. They really do. PCIe. Okay? PCI. Let me show you what the PCIs look like. They call them expansion slots. That's another name for them. These little cards, you put them into the expansion slots on the motherboard. And they come in, and they just a whole bunch of them throughout the history of motherboards. But we've kind of standardized now. Right in here is where you put a card, baby card, baby card, baby card, okay? Let's see, what do we have? What are the main ones that we use these days? Well, there's one that's just called PCI. PCI, old school. There's another one called PCI X. It's old.
PCIX.
The next one, the one that we use today is PCI, anybody? E, PCIe. Now watch this. Now PCIe has different flavors. One is called 1X, real small. I'll do it like that. How about that? You happy now? 1X. We have this 2X. Well, that'll be 2X right here. There's a 4X. Let's see, I'll put one in there. That's a 4X. I think there's a 6, but let's just jump to 8. There's an 8X. Maybe I'll let that one be 8X right here. 8X. Then of course, the last one is the main one that we use for graphics cards. 16X. So this would be a 16. This would be a 16. This would be a 16. 16X. And what I'm saying is, don't ask me about that. It's just a number. It tells you the length and a whole bunch of connectors. So I'm thinking that this is 16. Which one is this? It's kind of small. What is that? Don't tell me. It's interesting. I have to go into the BIOS UEFI. Anyway, 16, 16, 16. I'm thinking that's 2X. 3 2X's. Maybe that's 8. See, 8, maybe? Well, maybe 16. No. That's probably 8. I don't know. Okay. So we got the expansion. We know that in the old days, we used to have a chip right here that was called the North Bridge, and another chip that was called the South Bridge. And in between, we had these data lines pass, right? And they were just going all around the motherboard. You can look underneath the motherboard and you'll see it. But in the newer boards, we got rid of the North Bridge. We made the North Bridge become a part of the processor, the RAM, and one of these PCI slots for the video card, a fancy video card, not the play stuff. So now we only have this. This actually goes away. The North Bridge goes away. We have the South Bridge, big fat chip down here, South Bridge. Let's see if I can find it. Oh, I see it right here. South Bridge. North Bridge is gone, went away. It's built into the processor, memory in the back. It's all built into that, right? And then this is probably for the video card, right? Okay. Okay, let's see what else we got. Oh, you gotta have some Go juice, right? Yeah. This ain't gonna work without Go juice. I'd rather use another color. But anyway, we call this a power supply unit. PSU, and then we put one of those big black cables, thick cables, and we plug it. See, this is my picture of a plug.
No.
You like that?
Yes.
That's okay. you get an F, you'll be sorry. Just kidding. How about that? Now you have it? And? Okay, PSU. We know there's a big fat cable on that PSU. How many pins? 24. Yep, 24. We cooking with Crisco? Let's use another color. How about green? Because these cables look kind of crazy. So, stand by. We're just doing a quick review, then we're gonna go over the processor and RAM. I think that's the only thing we hadn't talked about. Okay, so PSU, power supply unit, you always have to give power to the motherboard. That's just this big fat 24 pin thingy. Okay, all right, Mr. D, I see what you're talking about. What you talking? Right here, 24 pins, and who else needs power? What other device on this motherboard needs its own power? CPU. So can we just wrap that bad boy up like this? It's usually a pin that's over here. How many? 4, 6, or maybe 8? 8 pins? You want to do 8? And? Okay. Who else needs power?
The PCIe.
Okay. You want to go ahead and put a video card in here?
Yeah.
Let's do that. Go away. All right. Here's a video card. How much did your video card cost, man? The one that you bought at Micro Center. How much was it? Give me a number. $700. $700 for this bad boy. $700 bucks. Now on side this card. And oh yeah, by the way, what's going to connect to it?
The monitor.
Yeah, the monitor. That's why you're doing it, so you can play games like Call of Duty. Kill Nazis. This is there. I get kids. I get tired of y'all. I get mad at y'all. I get mad at the kids. I get mad at the world. Pull up Call of Duty. After about 200-300 Nazis there, I'm feeling better. Okay, but I have to have a graphics card. Let me just say this. Look, let me just say this before y'all go talking crazy. There's a lot of stuff going on crazy these days. I say a lot of things to give you something that you remember and laugh about one day when you sit in a meeting and you say, sounds like something that crazy professor I say, right? It's to help you remember, right? So you ain't gonna forget this Nazi stuff when it comes to a graphics card. He's like, graphics card. That's what Mr. Darrell put in his machine so you can kill Nazis. I just say things to help get you to remember. Like I'll say something like, when we start talking about the internet, right? And the clouds, I say that's what you use the cloud for 2 things. That's what y'all use it for, porn and gambling. You won't forget that, will you? Okay, that's why I do it. Okay, so now we've got the graphics card connected to the monitor. Now this cable right here that's going to the graphics card is probably going to be HDMI, probably. Or it could be DVI or DisplayPort, huh? Okay, but the connector that we like, HDMI, right? Yeah. Okay. So that's the graphics card. That, getting back to what we were saying, brother, that needs some power right here. Usually 8 or 6. Let's do 6. Yeah, 1, 2, 3, 4, 5, 6. Oh, this is 6. I should make this 8. Sorry, my bad. How about that? And this is 6. So graphics card needs power too. So let's see. Power supply connected to the wall. 24 pin connected to the motherboard. Processor. If you got it, a graphics card. See, you may not even have a graphics card because you don't want to kill Nazis. Right? You just want to do PowerPoint or something. Nothing that's not graphics intensive. But I just put it in here so you can understand this is another name for this is a GPU, graphics processor unit, GPU. Somebody else needs power. Storage. Storage needs power. So I know I got to take a cable down here and and connect it to my storage. This is the power. Now these interfaces here are the cables that will connect the storage to the motherboard. I'm gonna use a different color so that you won't get them mixed up. Because that's what you're gonna do when we do the project. And I'm gonna say, that ain't gonna turn on. And you say, why not? Because you either forgot the power to the storage, or you forgot the cable, the interface, probably gonna be this, the interface that connects to the motherboard. It ain't gonna spin up. So storage always has to have power, and power supply, and it's gotta have an interface cable to the motherboard. We'll be doing SATA, little SATA cable. Come on now. I think we almost ready. Oh, what's missing? Got a monitor, what's missing? A rack, gotta have a rack. And what? Keyboard. And here's my rack. You know, it's kind of curved, like, you know, if you faint your hand, right? That's why I curve it like that. Okay, you know what? That's y'all's mentality, the cheap one. And now you happy? Cheap ones, right? Cheap mouse, $2. Okay, from Dollar Tree. Okay, I think we're almost ready, y'all. Oh, over here we got all these funky connectors, right? On the side, this side action right here. Right here. We did talk about that. Here, look. Side action. USB, audio, DVI, yeah, blah, 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 blah. Now remember now, we do have an HDMI on here, but we decided to go and spend $600, $700 for a graphics card to put here. So that means I don't need this one. Eh? Okay, that's just for people who don't want to kill Nazis. They just want to do PowerPoint and get on the internet. There's no need to buy this $600 graphics card when I can just connect my cable right here to my monitor. Come on now, can you visualize? It's called critical thinking. Do you want a job? Okay.
No.
I think we're ready. We've pretty much covered most of the stuff that will make this computer work. You know, we talk the case. You know, there's a case, right? You just ain't gonna have it sitting out like that, right? Dust, rats, roaches, bugs. You gotta have a case, right? Yeah, I think we're good. I think we're good. Okay. So let's talk about this cat and this cat. This is really what makes it go. Without a processor and without a brains and a desktop, we wasting our time. Usually I like to talk about this in the beginning, but for some reason, CompTIA decided that they want to talk about it last, so it makes no sense to me, but you know what? These days and time, nothing makes sense to me, so. Okay, so CPU and RAM. Let's talk about ones and zeros. You want to talk about ones and zeros? I think you should.
Talis is a global leader in cybersecurity, securing what matters most.
It's a common theme throughout the modern world that everything in a computer's brain comes down to ones and zeros. You've most likely heard that this code of ones and zeros is what's referred to as binary. And while almost everybody knows that this is somehow related to what computers do, very few of us seem to understand what binary is or why computers use it. If you want to know, then this video is for you, because it's actually a very simple concept and still quite fascinating. Before we get to computers, let's talk about what binary itself is, as it existed long before computers did. Binary is nothing more than a system of counting. To understand how it works, let's look at two other systems of counting, tally marks and the glorious base 10 positional that we all know and love today. Tally marks are the simplest counting system imaginable. However many things you have, you put down that many marks, easy as pie, but not very efficient. Meanwhile, base 10 positional, which is what we use today, uses a different symbol to represent different amounts of things. With the numbers 0 through 9, we can recognize that each symbol indicates a different amount of things. If we need to represent something higher than 9, we add a digit to the left, roll its first digit back to 0, and start over. This system is very efficient compared to tally marks because each digit we add exponentially increases the amount of things we can represent. Because in this system,
What he's saying here is what we do every day. It's like, what is he talking about? This is base 10. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Well, Mr. Dare, how'd you get 10? I went back to 1, right? Then I started with 0 again, right? No. We just do it every day. We never think about it, right? We know that after 9 comes 10. But we got 10 because we had to jump and move 1 over. The tens place, okay, now I see now, this is what y'all learned. This is that new math. The tens place, the hundreds place, the thousands place, 10,000s place.
100,000.
Oh, that's the kind of money you want to be making when you leave here, right? 100,000s place, and of course where I am, right? 100,000 is what? Million? I got mine. I'm finna retire. Bye. See you. I quit. Bye. Class over.
Woo.
Let me get that last check first. Then I quit. All right, so that is what we call the base 10. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Then you got to go back, jump to the next place, which is a 1. Then you start over with 0. Huh? Okay, that's base 10. Computers don't understand that crap. Computers understand only 2 things. What are they? Come on now.
Zeros and ones.
Okay, that's it. It's crazy, but you got to know this. That's all on and off. How about that? Isn't that a 1? If it's on, it's a 1. If it's off, it's a
0.
Hello. If there's current, if it's current, it's a 1. If there's no current, it's a 0. Is it making sense now? A computer loves that. Oh, you just turned me on. That's a 1. Oh, you just turned me off. That's a 0. Oh, I see some current that just came. You get a clock going. Current, current, no current, no current, no current, current, no. It loves that. This 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. I don't know that. Just give me a 1 and a 0. Power, no power, on or off, blah, blah, blah. Blah, blah, blah. Okay.
Then we add a new digit every 10 things. Each digit represents an increasing power of 10. This is the number of ones we have, the number of tens, the number of hundreds, the number of thousands, and so on. Now this is probably something you already know, but it's very important to keep it in mind when we talk about binary. Now binary works the exact same way as base 10 positional, but instead of each digit going from 0 to 9, it goes from 0 to 1. Counting upwards in binary sounds like this: 0, 1, 10, 11, 100, 101, 110, 111, and 1000. Because each digit of binary has only 2 values and not 10, each additional digit represents an increasing power of 2 rather than an increasing power of 10. So this is the number of ones we have, the number of 2s, 4s, 8s, 16s, 32s, 64s, 128s, and so on. Not nearly as efficient as base 10, but exponentially more efficient than tally marks. Literally. So now that we know how binary works, let's talk about computers. Why did the first computer creators, as wise and intelligent as they are, waste their time with such an...
Hold up. You mean to tell me these are dope smokers? I don't really know. I think they're just nerds. I just told you about the dope smoker because in California, surfing, Vietnam era, no, I don't want to go to Vietnam, all the poor people died. They don't want to go. So we're going to go to the university and play with the aliens, right? Smoke a little dope. Okay. That sounds much better than this. Boring. You feel me? You see where I'm coming from? So I guarantee you, later on, you're gonna think, Mr. Dare talked about the aliens and dope smoking. You ain't gonna remember this. But you're gonna remember the aliens and the dope smoking, right? No? Okay, whatever.
First computer creators, as wise and intelligent as they are, waste their time with such an ineffective system of counting. Well, it's because of a physical limitation on how computers work. Everything a computer does comes down to what's known as microtransistors. Simple, tiny, eensy-beensy little switches that can either be on or off and can be flipped on or off with a very weak electrical charge. The first goal was to get computers to count. And to get them to count by using these switches, we could use the tally system, meaning the number of on switches equals the number of things we have, or we could use the much more efficient system of binary, where each switch represents a digit of binary. 8 transistors using the tally system could represent a number as large as 8 by turning all of them on. With binary, we can represent a number as high as 255. An on switch means a 1, and an off switch means a 0. Now is a good time to mention that a single transistor is what's known as a bit, which stands for binary digit. A byte is 8 of these bits in a row, which means any number between 0 and 255. So if binary is just a system of counting, what do people mean when they explain how to spell things in binary? Well, what they really mean is how to spell things with ASCII. The American Standard Code for Information Interchange is a way to convert a computer's data, which can only be in numbers, and turn it into letters for humans to have an easier time to work with. ASCII simply assigns a character to each value.
Right here. So this is inside your computer. This is the software. This is the software doing this. ASCII is built into Microsoft, Linux, whatever, right? Remember now, computer understands ones and zeros. That is at the hardware level. Yes, sir.
What is the American Change Standard Interface word again?
Stand by. Computers only understand 1 and a 0. If you give me a page of a bunch of 1s and 0s, do I know what that means?
No.
Okay. That means I need a translator. I need something to translate all the 1s and 0s into some letters and numbers, like the 9. There's something called ASCII. It's built into the operating system and it's built into Microsoft Word and the browsers and all of these other applications. You don't know it. All you know is when you pull up your browser, you just see something you can understand. But behind the scenes, there is ASCII. It's something that the dope smokers came up with a long time ago. It's a chart that says if you get a 0, 1, 0, 0, 1, 0, 1, 0, that is the letter what? J. You feel me? It's built into the software. It's a chart. It's a chart. The number of zeros and ones, if it fits this pattern, it's a J. Tell me about K. What is K to the computer?
0, 100, 0.
Okay, you feel me? The only reason why we have this chart is for us. Now, if we were a computer, this chart would make no sense because we would understand 1s and 0s. Come on now. So we need a translator. ASCII is a translator. It's built into the software. Are you feeling me? You feeling me? There's another chart. There's another chart besides ASCII. Y'all gonna tell me what that chart is. What if I wanted an emoji? So ASCII only does a certain couple of things. What if I wanted to create an emoji? Is there a chart for emojis? Figure it out and you tell me. Let's continue.
Represented by a byte of binary. And because a byte has 8 digits of binary to work with, and 8 digits of binary can represent up to 255 values, ASCII had 255 letters and symbols to choose from, more than enough for the entire alphabet, punctuation marks, and other symbols. For example, the corresponding ASCII number for an uppercase A is 65. Now 65 in base 10 is equal to 1,000,001 in binary. So whenever you type in an uppercase A in a word program, a coding program, or a scripting program or whatever, somewhere there's a little tiny row of 8 transistors arranged in the pattern of off, on, off, 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 on, which represents 0, 1, 0, 0, 0, 0, 0, 1 in binary, which is interpreted as 65 at base 10, which is converted by ASCII into an uppercase A. You're likely starting to get a feel for the staggering amount of transistors required to write something as simple as a Facebook status, let alone all the different coding that your computer has to do to make the screen light up, play games, calculate massive values, and so on. Well, long before we got to the point where your phone can play three-dimensional games, it became clear that numbers as high as 255 just weren't going to cut it. Regardless of how many bytes we had, and it was a lot, even adding 4 fully active bytes together could only get a number as high as 1020. To solve this problem, new computers were designed to recognize 2 bytes as one single number.
Whoa!
So now instead of referencing one line of 8 transistors, computers could reference 2 lines, giving 16 digits worth of binary. This was a huge help because it increased the amount of representable numbers exponentially from 255 up to 65,535. When you hear people talking about the difference between 8-bit and 16-bit, this is more or less it. Now that doesn't mean that a 16-bit system is exponentially that much more powerful, because your program isn't always going to be utilizing all of these numbers in each byte that it represents. It just has the option to, which opens up lots of doors. Well, this could go on for ages and ages, but I want to end this particular video right here so as not to be overwhelming. In future videos, I will explain how computers use these numbers to decide which pixel is what color on your monitor, what the different components of your computer are for, and how hard drives store binary digits on a spinning disk rather than in transistors. Thank you for watching, and if you enjoyed this video, liking and subscribing is always a huge help.
Yep, we do. Already done it. Okay. Do this one. No more yapping. I'll let you do it.
The industrial grade products you need. Granger, for the ones who...
Okay, here we go.
I remember when agents, they did.
Binary, a numbering system where all possible values are represented by 2 symbols, like on-off, true-false, or 1 and 0. Computers handle all data as a stream of binary numbers, because from a hardware perspective, it's much easier to represent 2 values with a transistor as opposed to 10 values with that system they taught you in school. It first appeared in ancient Egypt with Horus-I fractions, and is used independently in many other cultures, like for the I Ching in China, and is the basis for Morse code, where every letter of the alphabet is represented by 2 different sounds. When the first computers arrived, they were programmed by manually flicking switches or with punch cards used to represent binary values. Today, modern microchips use Boolean algebra to combine logic gates like and or not to execute binary code billions of times per second, allowing you to share silly videos with your friends on the internet. A single binary digit is called a bit, which is either a 1 or a 0. You can't do much with a single bit, so they often come in a package of 8 called a byte that can represent 256 different values. Modern programmers don't write binary directly. Instead, we write code in a high-level language like Python or C++, which can then be interpreted or compiled into a binary format. However, you should
See that? What he's saying here is there's a programming language that you can write, you can see on the screen when you're coding, right? That will convert it to those 1, 0, bit into that code, built into that Python. I just say Python, because we love Python in cyber. You gotta learn Python. You gonna take a class in Python? You ain't ready. Okay, so for those who want to do something in cyber or IT, you doing Python coding, right? You can read it, A, B, and C, 10, 9, whatever. But that Python with the operating system is going to convert it to 1s and 0s so the computer understands it. So that this cat, I'm going through this is because this cat right here is the key. This cat, CPU, is the mamma jamma. And it only understands one language, and that's binary. So before we can really talk about this process, we gotta make sure we understand binary, 1s and 0s. And I can get you there if you listen to me. Okay, done. Continue.
format. However, you should still know how to count in binary to impress your friends. In the base 10 system, you have 10 different symbols. When you get to the number 10, you add an extra digit, then another one for 100 and 1,000 and so on. This is called positional notation, where each position represents a value 10 times greater than the position on its right. Binary works the exact same way, but because we only have 2 symbols to work with, the position on the left represents a value that is 2 times greater, like 1, 2, 4, 8, 16, 32, 64, and 128 in a byte. To get a its corresponding decimal value, we multiply 1 by its place and then add them all together, which in this case would equal 123. In a computer, these binary values are mapped to something more interesting for humans, like a letter of the alphabet in an ASCII table or the color of a pixel in an image. Now, because binary is so hard to read, you'll often find it converted to hexadecimal format, which is a base 16 numbering system, using the symbols 0 through 9 and A through F. Conveniently, each hexadecimal digit can represent 4 bits, which is also called a nibble. A low-level programmer might take a hex dump to analyze the raw data of a file. It's in hexadecimal format, but each pair of characters represents 8 bits or 1 byte. This has been binary in 100 seconds. If you want to see more short videos like this, hit the like button and subscribe. Thanks for watching, and I will...
When we start talking about network cards, we're gonna come back to this. We're gonna do 3. How do I say this? What's it called? We're gonna talk about base 10, base 2, and then base 16. And we'll do some examples so you understand that. You got to know this if you want to do Net Plus. Some of y'all already did it. Y'all, if you take my stuff, you're gonna learn this. You're gonna learn it. So I'm gonna teach you about base 10, then I'm gonna teach you about base 2, and then I'm gonna teach you about base 16, because you have to understand those 3 numbering systems in order to really be good at what you want to do. Foundation. Okay, now we can start going back to these processors. We can go to the processors.
Processors are all about speed, but how exactly do they work? In this video, we go into detail about what a processor is, explain how it works, and go over its main features. The processor is a chip responsible for calculations. It makes all the logical decisions, which are basically all the tasks your computer does, from the simplest thing as open a window, to the most complex, such as completing a 3D animation. For this reason, the processor is known as the brain of the computer. To understand how it works, imagine this scenario. We have a processor, and next to it there is memory RAM, and inputs coming from the output devices, your hard drive, mouse, keyboard, and monitor. The mode of communication between them is called the motherboard. The motherboard is responsible for linking the processor to all the components of your computer. The processor executes 3 basic functions: receive input data, process this data, and provide output data. But what exactly does all this mean? When you type in some text, for example, each letter entered is input data. The processor receives this data, processes it, and provides the output. In this case, everything that you type will appear immediately on your screen. This all happens in a fraction of a second. There are other types of processors too, which may be installed on your system, but every processor contains several important features. Here are the main ones. The socket. The socket is a type of physical connection between the processor and the motherboard, and it is responsible for transmitting energy to the processor. The core. The cores are responsible for the processing speed. The more cores a processor has, the more functions it can execute simultaneously without overloading your system. The clock. The clock is responsible for defining the frequency that your processor will use to execute one task. It's measured by hertz. This means the amount of cycles that can happen in a given amount of time, in this case, in seconds. For example, if a processor has a 2 gigahertz clock, it can have up to 2 billion cycles per second. So the higher your clock frequency is, the lower the execution time will be, which for you means a faster processor. The cache. Basically, the cache is the auxiliary memory of a processor where the most accessed data that will be processed is identified and then stored. The processor accesses this memory and is able to execute the action faster because it's more readily available. This is one more important factor that has a direct impact on the processor speed. The more cache there is, the more quick storage capacity you have, which results in a faster speed. Anytime you need help or have any questions, you can always contact us through social media.
Okay, Mr. D. Okay, I see what you're talking about. What you talking? All right, let's see what we got. We got the socket, right? The socket is where you place the processor. The socket. So I just did it like this. So I already put my processor on the socket. We good? Okay. Now, in a second, I'm gonna tell you about what's inside this processor. See what's inside this processor. Here's the processor right here. Right? See it? You see it with your eyeballs. There it is. If you take this bad boy and turn it on its side, get a real thin laser beam and slice it down like zip, and cut it in half. Not cut it in half like this. Turn it on its side. So turn it on its side. Here, turn it on its side. Here's its side. You see it? Now you cut it. Then you use a microscope and you look to see how many cores. Actually, the cores is the process. This is right now, this is just a chassis. It's just a case. In the old days, when I was coming up with computers, this was one core. Talk to the aliens. What I'm doing now is I'm taking this case and I'm putting little computers inside. It's always in twos. Base 2. So I can have one, but you're not gonna have one. It's always gonna be 2. And what do you think? 1, 4. 2, not 6. Yes. Remember? Remember now. Base 2. 1, 2, 4. You always double. 8, double.
16,
16,
32.
double. 32, double.
64.
Yeah, I could be wrong, but I think we might be supercomputers are different. I think the ones I've seen, all the way up to 128 cores. That's some fast stuff, right? What I'm saying is 128 cores. Are you with me? Are inside this chassis. And how do I know this? Because I turn it to the side, I cut it, I put it on the microscope. I'm like, ooh, I see 128 cores. That's a dope smoke. How did you get 128 little processors into this little thing? Alien technology? Okay, so now that's our core. That's our core. We like a core. Let's go to something that I can understand. Let's do 4 core. Can we just do 4 core? Okay, so I got 4 core. That's old school, to be honest with you. Boy, that's an Intel i3 or was it 3i or i3, right? 4 core? 4 core. Now, let's talk about cache. Here we go. I told you about the desktop. That's the RAM. Come back to that in a minute. Is the RAM. It's your desktop, right? The brain, these cores are making calculations. And I told you that when it makes a calculation, it has to store the results somewhere. So I told you earlier that it takes that result and sends it to the desktop, which is RAM. That's inefficient. Because what if I told you that once I make a result, I need to take that result real quick and add it with something else. So that means I have to wait, bring it back up, go and get something else, bring it up, calculate, send it back out to RAM. We did something faster there to make this thing go fast. This didn't take any dope smoking on this one. Even my son can come up with this. Say, Papa, why don't you just take some of these chips right here and put them real close to the processor? Not a whole lot, just enough so you can do some work. In other words, here's my table. Then maybe I have a little scratch pad right here to put my stuff on. So I can work real quick, go grab it, make another calculation, put it right there. And when I finally finish, then send it to RAM. What you think? That's called cache. Cache can be in 3 places. Stay with me. Cache can actually be inside a core. Cache. It's memory. It's RAM. Want to call it baby RAM? Cache. We call that, if it's right here inside the core, that's called L1. With me? What if this cat needs to talk to this cat? Because they talking, right? Hey, you process that, I process this. And then we need to put it somewhere. Where can we put it? So we both can get to it. L2? L2. And now this is all inside the little chassis. You don't see all this because you ain't cut it in half yet. So maybe I have some L2s out here. L1s will be inside the core. The L2s are outside, but they're still inside the case. Are you with me? I could also do another one, L3. L3, what do you think L3 is? Right out here, real close. L3 might be right here. Huh? It's called cache. L1 cache, L2 cache, L3 cache. Yes, sir.
So it's not like it's actually CPU at all, is it?
The L3? Yeah, well, you know, it's on the motherboard. Yeah, it's soldered in. Yeah. Right here, it's on the motherboard, and there's some lines that go in here. You feel me? What do you think? So if you see L1, L2, L3, think cache. Yes, sir.
So L3 cache is on the motherboard, but like, does the CPU get like determine how much of that you have or something like that?
Well, you'll see it in the specs. The specifications for a computer will say something about cache, 128K or something like that, 16K. That's what they mean. All right, they're probably telling you about this cache right here. Then I raise be like, man, I don't know. It's been a while since I looked at specs for anything. I just go with the flow. But anyway, all I know is that if I see something that says, when you want to buy something from Dell or HP, it'll say processor, i7, blah, 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 128 cache. I'm like, oh, cache. That tells me it's something L, probably L3. What do you think? Am I answering the questions or am I just yapping? You got the L down? You ain't gonna get that from nobody else. So you owe me money. You need to pay me him, pay. I want some coins. I ain't gonna say, I ain't telling anybody anything. I ain't gonna do this one. I wanna do it, but ready. 922. Let's do this. Spinning buses, rams, and that's it. Okay. 922. How big is, how fast is this? Is this long? 4 minutes. Let's do
Hey,
it.
real quick, how would you find the answer in all this data?
We're gonna do threading, we're gonna take a break, we're gonna come back and finish processor, we're gonna do memory, and then one lab, and then we go. How about 10:30?
The volume.
Yes, sir. Thank you. Let's do a break right after this. All right, we ready to go. We gotta let's do this threading because this is a hardware class. We gotta do threading.
Hyperthreading. Now, hyperthreading is a technology developed by Intel that increases the performance of the CPU cores. It enables multiple threads, which are sequences of instructions, to be run by each core to make the CPU run more efficiently. And by doing this, the CPU can perform more tasks in the same amount of time. So in a nutshell, you can run a lot of applications at the same time while maintaining the performance of your computer when you have a hyper-threaded CPU. In other words, your computer is not going to slow down. Now, in the beginning, a CPU will have a single core, and a core is a unit that reads and executes instructions. So later on, manufacturers started to add additional cores to a CPU so that the CPU can read and execute more instructions at a time, which dramatically increased the performance of the CPU. So for example, here we have a dual-core CPU, which basically means that it has two physical processing units on a single chip. Now, to further increase the performance of this CPU and to make it faster even more, Intel introduced hyper-threading. So if hyper-threading technology was added to this CPU, for each physical core that's on the CPU, the operating system will recognize each physical core as two virtual or logical cores. So basically, hyper-threading virtually doubles the amount of cores that are on the CPU. So this dual-core processor will be recognized as having 4 cores through the lens of the operating system. Now keep in mind that hyper-threading doesn't double the physical cores in the CPU. It only doubles them virtually or logically.
Sound like some matrix.
And since the operating system will recognize each physical core as two virtual cores, the operating system will schedule or share the workload between them. Each virtual core can be individually interrupted or directed to execute a specific instruction that is independent of the other virtual core. So that is the main function of hyperthreading, which is to increase the amount of independent instructions in the pipeline. And by doing this, it will eliminate any idle time on the CPU, which makes the computer run faster and more efficient. Now, it's also important to note that in order to take advantage of hyperthreading, you have to run applications that take advantage of multi-threading technology. Heavy applications such as video editing and video encoding will take full advantage of a hyper-threaded CPU. But lighter applications such as loading a web page, you're not going to see much of an advantage of having a hyper-threaded CPU. Hyperthreading was first introduced by Intel back in 2002 and debuted on the Intel Pentium 4 CPU and Xeon processors, and is still used today. In fact, I'm currently using an Intel i7 quad-core CPU on my personal computer, and it also has hyper-threading technology. And if I open up my task manager, my operating system will recognize that I have 4 physical cores and 8 logical or virtual cores.
Ooh. Okay. Are you finished? I'm gonna try that right quick. Now, what did you say I needed to do? Go down here to do task manager. Okay. And then what do I do now? For you brainiacs, what do I do? Something over here.
Go to
This one right here. And then click this one.
and it's right there.
How many sockets? One. That's like common sense, right? One socket. This how many cores?
6.
Physical cores.
6.
How did you get 6? Wow. Should have been 8. Just made a liar out of it. Okay. So how many logic? 12. Operating system thinks it sees 12 cores, but in actuality it's 6. I just learned something new. I gotta stop saying that. Okay, fine. Okay, cool. So we understand hyperthreading. So why don't we do this? Let's stretch, come back, and we're gonna wrap this up. We're in phase 2. So take a stretch, take a squat, whatever you got there. Come back in about 5. Let's just do 5 so we can hurry up and get out of here.